At the end of the last video, we had created a diagonal matrix with the eigenvalues running down the diagonal, and this section is going to build on that. We'll see a couple of special cases and some other views of creating diagonal matrices. So I typed up a couple of things at the beginning so you don't have to sit here and watch me write stuff. The goal of diagonalization is you want a matrix that is similar to the given matrix. So if you're given matrix A, you want to find a process of doing P inverse times A times P to get this new matrix that is similar to the original matrix. To do that, the first thing you have to do is find the new basis, right? You can't find the matrix P without finding the new basis. The new basis will make it diagonal. This comes from the eigenvector. So if you follow that eigenvector process, you will create a specific basis that when you run it through a similar matrix equation, it'll give you a diagonal matrix. If two matrices are similar, it turns out they have the same eigenvector. So if you do P inverse times A times P, the new matrix that you create and the old one have the same eigenvectors. The last one is kind of important when we go to set these things up. If you've got an n by n matrix, it's diagonalizable if and only if it has n distinct linearly independent eigenvectors. So we had done an example a couple of sections ago where we had a 2 by 2 matrix, but we only came up with one eigenvector. No good. You can't do that because you don't have the same number of eigenvectors as you have rows or columns in your square matrix. The other thing is if it turns out that you come up with two eigenvectors that are linearly dependent, then no. Unless you have n linearly independent eigenvectors, then you can't diagonalize the matrix. Let's start with a 2 by 2 just to run through the process one more time, and then we'll get to the good stuff. So let's say I've got matrix A as the matrix negative 14, 12, negative 20, 17. And I want to diagonalize matrix A. So the first thing is I need the eigenvalues. Okay. Remember how to find the eigenvalues? That's the determinant of lambda I minus A is equal to 0, sometimes also called the characteristic polynomial. So lambda I will give me lambda 0, 0, lambda minus negative 14, 12, negative 20, 17, and that gives me lambda plus 14, negative 12, positive 20, lambda minus 17. Now the determinant. Ooh, we got some big numbers in here. We've got a lambda plus 14, lambda minus 17, and then minus a negative 240 is equal to 0. So I work this out. I get lambda squared minus 3 lambda. If I multiply 14 times 17, I get negative 238 plus 240. This will be okay. I'm going to try to carry this across here. Lambda squared minus 3 lambda plus 2 equals 0. So I factor this. Lambda minus 2, lambda minus 1. I check my work because it would be embarrassing if I get the whole rest of the problem wrong just because I factored it wrong. So lambda squared minus lambda minus 2 lambda is minus 3 lambda. Negative 2 times negative 1 is 2. That's the answer to my first part of my question, is that lambda equals 2, lambda equals 1 are the two eigenvalues that correspond to that matrix. Now the second step is find the eigenvectors that correspond to each lambda. All right, so this is where we do that lambda I minus A, and then we drop the zeros down the column because we're trying to set it equal to 0. So for lambda equals 1, lambda I gives me 1, 0, 0, 1, minus the original matrix, negative 14, 12, negative 20, 17. All right, so that gives me 14, negative 12, positive 20, negative 16, and then, no, 1 minus a negative 14 is 15. We drop in our column of zeros, and we row reduce it. So if I divide the top row by 3, 15 divided by 3 is 5. Negative 12 divided by 3 is negative 4. On the bottom row, 20 divided by 4 is 5. Negative 16 divided by 4 is negative 4. Hey, I got the same row twice. So this gives me 5, negative 4, 0, 0, 0, 0. And I set up my parameters. X sub 2 is t. So x sub 1 is going to be 4/5 of t. Because I move the 4 over the other side and divide by 5. Maybe it would make it easier if I multiplied through by a 5, and so I got 4, 5 as my first basis vector. Okay, now let's do it for lambda equals 2. For lambda equals 2, I get 2, 0, 0, 2 minus negative 14, 12, negative 20, 17. And what does that give me? That gives me 2 plus 14 is 16, negative 12, positive 20, 2 minus 17 is negative 15. All right, so divide the top row by 4. I get 4, negative 3. Divide the bottom row by 5. I get 4, negative 3. Drop in your zeros, and you realize that this simplifies. 4, negative 3, 0, and a row of zeros as we expected. That makes x sub 2 t. X sub 1 then is 3/4 t. We could write 3/4 in 1, but why not write the second vector as 3 and 4? All right, now we're going to take those two vectors and we're going to assemble them into matrix P. So assemble the eigenvectors into matrix P. So the first column is going to be 4, 5. The second column is going to be 3, 4. You could put the fractions in there, but why? All right, next step, find P inverse. Let's start with the determinant of P. The determinant of P will be 16 minus 15. Couldn't ask for a better determinant than that. That means that P inverse is just flip the 4 and the 4 that's already there. This becomes a negative 5. That becomes a negative 3. And my last step is to multiply P inverse times A times P. So here's P inverse times matrix A, which was negative 14, 12, negative 20, 17. All right. So 14 times negative 4 is negative 56, and then plus 3 times 20 is 60. So I should end up with a 4. All right, 48 minus 51 is negative 3. 14 times 5 is 70. Minus 80 is negative 10. And I get negative 60 plus 68. So 8. Okay. Now, let's take that times matrix P. So let's take 4, negative 3, negative 10, 8, and multiply it by 4, 3, 5, 4. So this gives me 16 minus 15, which is 1. The outsides give me 12 minus 12, which is 0. Negative 40 plus 40 is 0. Negative 30 plus 32 is 2. There it is. My diagonal matrix. Lambda's down the diagonal, and it's all good. All right, let's try this for a bigger matrix. Let's try this for matrix A equals 0, 0, negative 2, 1, 2, 1, 1, 0, 3. I want to diagonalize. So the first thing is I got to do lambda I minus a. So if I go down the diagonals, lambda minus each of those is going to give me a lambda minus 0, which is just lambda, lambda minus 2, lambda minus 3. All the others will just be opposite signs. So 0, 2, negative 1, negative 1, negative 1, 0. Okay. There's my lambda I minus a. Let's go ahead and find the determinant. So I'll get lambda times the 2 by 2 in the bottom right corner, which will be lambda minus 2, lambda minus 3. The second piece will just be 0. And then the third piece will be 2 times 0 minus a negative 1 times lambda minus 2. All right, so going across the top row knocks out one of those three pieces. All right, so now I need to set the determinant equal to 0. This gives me lambda, lambda minus 2, lambda minus 3, plus 2 times lambda minus 2 is equal to 0. Again, like we did in the previous case, I would factor out that lambda minus 2 because otherwise you're going to have to do one of those synthetic division deals where you get a third-degree polynomial and you have to start working your way backwards with the rational root theorem, going, all right, I can try this, I can try that, I can try factors of the third term divided by the first term, and so forth. So let's avoid that if we can. Lambda minus 2, and we're left with lambda times lambda minus 3, which is lambda squared minus 3 lambda. And then if I factor out a lambda minus 2, I'm just left with a 2. Oh. So I get lambda minus 2. This inside piece factors as what? As lambda minus 2, lambda minus 1. So that'll give me a lambda squared minus 3 lambda plus 2. Hey, we end up with the same factor twice. So I end up with lambda minus 2 squared times lambda minus 1 equals 0. So I got two eigenvalues. Lambda equals 2 with a multiplicity of 2, and lambda equals 1 with a multiplicity of 1. Now, I've got to find the corresponding eigenvectors that go with each eigenvalue. I'm going to start with the one that has a multiplicity of 2, because if this thing doesn't produce two eigenvalues, my problem's over because it's not diagonalizable. If it does produce two eigenvalues, then we're okay. But remember, for a 3 by 3 matrix, I need 3 eigenvectors, not necessarily 3 eigenvalues. I need 3 eigenvectors. So let's do lambda I minus a. So I'll get 2, 0, 0, 0, 2, 0, 0, 0, 2. There's my lambda times the identity matrix, minus the original matrix, which was 0, 0, negative 2, 1, 2, 1, 1, 0, 3. All right, what do I get? I get 2, 0, 2, 1, 0, negative 1. Nope, negative 1, sorry. And then 0 minus 1 is negative 1, 0, negative 1. Hey, this is good, because you notice all three rows are scalar multiples of each other. So now I can reduce the first row just to 1, 0, 1. The second row and the third row collapse into that first row. This means I need 2 parameters. And that's good, because 2 parameters will give me 2 eigenvectors. So let's let x sub 3 be t, and let's let x sub 2 be s. Then x sub 1, because I'm going to add my column of zeros over here. X sub 1 plus x sub 3 is 0, so x sub 1 is the opposite of x sub 3. Okay. Separate these. All right, so if x sub 1 is negative t, x sub 2 is s, x sub 3 is t. That gives me 2 vectors, one with the s's and one with the t's. So for the s's, I have no s's in the first one. I have one s in the second, no s's in the third. For the t's, I have negative 1 in the first spot, 0 in x sub 2, and 1 in x sub 3. So this produces two eigenvectors, right? These two things are the eigenvectors. All right, so now I'm relatively convinced that if I do this now for lambda equals 1, I'll be able to find another eigenvector that then finishes out the problem. So for lambda equals 1, I end up with 1, 0, 0, 0, 1, 0, 0, 0, 1, subtract 0, 0, negative 2, 1, 2, 1, 1, 0, 3. Okay, that gives me 1 minus 0 is 1, 0, positive 2, negative 1, negative 1, negative 1, and then 0 minus 1 is negative 1, 0 minus 0 is 0, 1 minus 3 is negative 2. So this time it's the first row and the last row that are multiples of each other. So this gives me 1, 0, 2, 0. Let's call this 1, 1, 1, 0, and 0, 0, 0, 0. I can actually do a little bit more row reduction on this to get rid of some of those elements in the second row, at the very least to clear out one of them. And so when I do another row reduction, that gives me the first row still the same, 1, 0, 2, 0. The second row becomes 0, negative 1, 1, 0, and the last row is a row of zeros. So it looks like here I can start with x sub 3 as t. That means that x sub 2 is also t, right? Because that'll give me negative t plus t is 0, and then x sub 1 is negative 2t. Right, so I got negative 2, 1, 1. All right, next step, matrix P. Matrix P is composed of the three eigenvectors, 0, 1, 0, negative 1, 0, 1, and negative 2, 1, 1. By the way, it doesn't matter what order you put those eigenvectors into matrix P. If you put them in a different way, then all that's going to happen is you're going to change the order of those lambdas going down the diagonal. So at this point, if I had a lot of time, and you had a lot of time, we could sit there by hand and figure out the inverse of matrix P, right? We could put the identity matrix and the matrix and together and row reduce and get the identity on the other side, or we could set up adjoints and cofactors. But in this case, I'm going to do a little hand waving here and do P inverse times A times P. So when you do this on a test, I'm going to expect that you work through the whole process, find the eigenvalues, find the eigenvectors, assemble them into a matrix, and then I'm going to expect that your answer matrix matches the matrix P that you're giving me. So when I do P inverse times A times P, these first two vectors over here came from lambda equals 2. The last vector came from lambda equals 1. So I would expect then that the answer would have a 2, and a 1. Right? If you swap this and you put that lambda equals 1 first and then the other two, then your matrix would go 1, 2, 2 down the row, or down the diagonal. All right, let's try another one. Suppose I give you this matrix. Matrix A is 1, 0, 0, 1, 2, 0, negative 3, 5, 2. Start by finding the eigenvalues. Determinant of lambda I minus A equals 0 to get your characteristic polynomial. So I got a lambda minus 1, 0, 0, negative 1, lambda minus 2, 0, change sign, lambda minus 2. All right, this turns out to be pretty easy because look what happens up at the top. There's only one value that's going to give us anything interesting, that lambda minus 1. And then when you do the 2 by 2, you get lambda minus 2 times lambda minus 2 minus 0. The other two pieces here, that A12 and A13, just produce zeros. So it turns out I get lambda equals 2 with a multiplicity of 2 and lambda equals 1. I'm going to start first with that lambda equals 2, just because, like I mentioned at one point, if you don't get 2 eigenvectors out of that, then the problem's done. So let's do 2i minus a. That gives me the identity matrix times 2. Subtract the original matrix, which was 1, 0, 0, 1, 2, 0, negative 3, 5, 2. All right, let's see what we get. 2 minus 1 is 1. Couple of zeros. 0 minus 1 is negative 1. 0, 0. And then the last row is going to give me a positive 3, negative 5, 0. All right. What does that tell me? That tells me that the second 2 rows will combine together, and I could write this as 3, negative 5, 0, tack on my row of zeros, a 1, 0, 0, 0, and then a row of zeros. When I row reduce it, here's what's going to happen. I'm going to get 1, 0, 0, 0, 0, 1, 0, 0, and then a row of zeros. This is only going to produce one eigenvector. And that eigenvector is going to be x sub 1 is 0, x sub 2 is 0, x sub 3 is the parameter, so 0, 0, 1. Not enough. So, not diagonalizable. Why? Because I had a 3 by 3 matrix, I should produce 3 eigenvectors, and I didn't. The only other thing that I want to mention in this video is setting up a matrix for diagonalization using a linear transformation. So I just want to set one up for you. I'm not going to run through the whole process because we've been through a few of these already. But suppose I've got a transformation that goes from R3 to R3, and it's defined like this. The transformation maps x, y, z onto negative 2x plus 2y minus 3z, 2x plus y minus 6z, negative x minus 2y. And my goal is to find a basis for the domain of the linear transformation. So the matrix for T relative to that basis is diagonal. So how do I set this up? I need a matrix for the transformation. So 3 by 3, I'll put the x's, the y's, and the z's like that. So now look at the x's. Negative 2 for the first, 2 for the second, negative 1 for the third. Look at your y's. 2 for the first, 1 for the second, negative 2 for the third. Look at your z's. Negative 3, negative 6, 0. Diagonalize that. And your answer will be the matrix T, but relative to the new basis. What is that new basis? That's the basis formed by the eigenvectors that you're going to find as you go through this process. And that's the end of this video on diagonalization.